Very good. Thank you very much for the warm welcome. I would like to today discuss human education in an AI age. What is it that we as people now need to be educated in as we enter this new industrial revolution that is upon us at this time? So that's why I've entitled my talk, Fixing Human Education for the AI Age. And the central question you really need to start to ask is, given the real world has changed, how should education react? What should change in what we learn? And I'm talking school systems right through to college. What should our children learn, and how should this be affected when the outside world changes? And it's changing now extremely rapidly. So look, my day job is I build technology. Some of you will be familiar with Wolfram language, Mathematica, and Wolfram Alpha. These are, in a sense, computational technology, and traditionally this was running many different kinds of simulations and models, lots of things with data. What we're trying to do is build the ultimate way to deploy computation in any walk of life. And this has changed, again, dramatically over the last 36 years. So 36 years ago, when we started the company, people said, how could you base a company on math? You know, you're crazy. Only a few people do math. They do it in research departments. Now, computation is everywhere in the world. Virtually every board of every company is worrying about data science, about modeling, about AI. These are all parts of computation. So in a sense, we've moved in 36 years from a very specialist mathematics that just drives a few parts of what we do to computation for everyone, virtually all the time. So this is a major change in the world that, in a sense, Wolfram and computation have sort of been intertwined for 36 years. So right back in 1988, when we launched, we were on the Next machines that Steve Jobs pioneered, and he in fact came up with the name Mathematica and was at our launch event. And then walk forward to 2009, and we had the first sort of symbolic AI of Wolfram Alpha. And we sort of invented this idea of symbolic computing so that you can represent everything in a common way, whether it's data or computation. And then we were the first, one of the first plugins for ChatGPT when that arrived. And now we're sort of working hard on hybridizing computation with AI. And we sort of end up as both a technology company and a consulting organization. So that's sort of what we've been doing around computation. So here's what I have to report. If you go to the end of 2022, just before everybody got onto generative AI, this is where computation had got to in the world. So there were subjects that were always computational. Maths itself, physics, accounting. Hundreds of years you've applied computation to those subjects. How do the planets go around the sun, for example? Then there were subjects that were already fairly new to computation, but they were existing in 2022. So programming. Programming is in the current form, is a thing you do since computation arrived. Data science, social media, and of course I put in red, AI. The third column is very interesting. It's subjects that existed before, but there's now a computational version of those subjects. So biosciences. People did biosciences for many years, but now there's computational biosciences that allows you to work out much, much more than you could before. Even things like history and archaeology, medicine, of course, marketing and business. These are subjects that in the last decade or two have gone from very qualitative subjects to very quantitative subjects. But the kind of quantitative you need is very high-powered. Most of the things in the third column, you need to have much more sophisticated mathematics and computation to do a good job with them than you do in the first column. But the real point is, even at the end of 2022, most decisions in the world depend on computation. From the pandemic to other things, people are much more computational than they were just a few decades ago. And just to point this out, here's a typical example I like to show. I'm going to try and find out where the sequence occurs in the human genome. So as you know, there are 4 base pairs, and I'm going to try and evaluate this. And oh my goodness, I guess something's happened here. I think I may be off internet. That's always a bad sign. So maybe let me just quickly see if I can reconnect, and if not, we'll skip over this. But what I was trying to show is normally I can directly, I think it's failed to get the information. I can directly go to and actually just compute directly out of this a sequence out of the human genome and find where that is. And the fact that I can compute that directly is a sort of new facet of computation, particularly when it's working nicely. I'll come back to that a bit later. Hopefully I'll get it working. So, as I was trying to show, in 2022, we were at a stage where you could deliberately compute many things across many fields. So what's changed in 2023? We now have essentially high-level computation everywhere, but it's also potentially accessible to everyone. As opposed to it just being available to people who are good with computation, now potentially anyone can access it in all fields. And that's the potential interface we have of generative AI connected to computation. So in a sense, that's the background. Let's get back to education. That's what's actually happened in the real world. How must education reflect this change? Well, 3 changes. Firstly, it's got to actually follow the real subject. And the real subject, certainly around mathematics, is that you have computers doing calculating. So we'll come back to that. You've also got to use modern machinery. It's no use using machinery which existed 100 years ago instead of modern machinery when you're trying to learn something, because the machinery affects how you do things. And the other thing we need to understand is, where is the human adding value? And where is it just, really, you should leave it to a machine? And these are all things we need to think about hard for education. So, very important not to confuse, when you discuss education, what we need to learn from how you learn it. So I go to many education conferences, and they get obsessed with how you learn the existing subjects. But that's not reflecting what you need to know. There's a real world that changed. You need to change the actual subject, not just change how you teach the existing subject. And so there's a big difference of what we need to learn, not just how we learn it. And computation and AI changes both. But the one I really want to focus on is it changes the subject itself. And that's sort of critical. So I want to talk about maths, because I know a fair amount about it, but it's also for another reason, that maths in schools is at the epicenter of the problem. Let me explain why. So people think, governments, employers, universities think that maths is, quotes, the most important mainstream subject for the AI age. Also, when you take an exam, people say we can agree about the marks for the exam because the answer was right or wrong. If you take an exam in, let's say, English literature or Polish literature, and people maybe disagree about how to mark it. It has a huge number of learning hours invested in it, and yet it is more different from the real world than essentially any other mainstream school subject at this time. It has many students connected with it. Most people in this room will have spent many hours a week for many, many years of their life studying mathematics. Now, my news here is, if by the time you're about, in most countries, 16, 17, 18 years old, the subject you're studying, in my view, is about 80% wrong or misoptimized from what it should be. So it's a big it's not just a little bit wrong, it's very substantially wrong. And let me explain why I say that. It's very simple to explain, actually. So the problem is there are no computers for computing in the maths curriculum around the world. So in real-world maths, the thing I was describing that we do in the real world, computers do almost all the calculating. That's the world we live in. The hint is in the name. They're called computers because they're very good at it. They compute things very, very fast, much, much better than humans. In educational maths, people do almost all the calculating. And that's the disconnect. They're pretty much different subjects. And that has much worse consequences than you might think. People say, well, it's okay, we could just learn how to do that first and then we'll use a computer. But actually, it's much worse than that. So the mainstream need for the AI age is that we have people who can think, what I call think computationally. And I sort of describe this as, at the top end, being computational thinkers, and the thing you do all the time is computational literacy. You need to have sort of a way of thinking about life, a way of interacting with life that you can just do everything at every level in the population. But the aim of this is people make better decisions using this power of mathematics that's come up over hundreds of years and now has machinery that can really drive it into every area of society. So that's what we need to achieve, in my view, in the mainstream curriculum, and we haven't. So let me describe that a little bit more. So there are really 4 steps to the process, this magical process of mathematics or computation. You start by defining the problem. So what does that mean? Well, we could say, for example, in this room, let's suppose we could lock off all the air conditioning and make it airtight. How long could I speak before everyone literally dies of boredom? That would be a defining problem that we might want to take, and then we might want to abstract that to a piece of mathematics so that we could actually work out, in a sense, a way to compute that answer. And so that would be the abstraction state. You might end up, let's say, with an equation or an expression there. The third step is to compute it. So you say, right, this was the thing I set up in a mathematical form, and now I want to take it to the answer in a mathematical form. Let's say x equals 3. And then the final step is you say, right, x equals 3, what does this mean? Maybe it means 3 hours. And does this make sense? Is this the right answer? Did I make an assumption that was wrong? Et cetera, et cetera, et cetera. So this is the process that has driven our modern age, running this process in a sophisticated way. But the key thing to understand is the reason you want to abstract is because you can take so many different situations and turn them into this very precise way. We have many, many ways to work out an answer that we now have machines to move to an answer. So this is why abstraction is a very important step. What's the problem in education? Well, basically it's this, that we're spending almost all the time doing step 3 by hand on very simple problems. What we should be doing is spending much more time using computers for step 3 almost universally, and using people for doing much more of steps 1, 2, and 4 on much harder problems much earlier. So I actually think the thing needs to get harder when you use computers. Actually, there's a slight change, because since AI, we have the computer helping more with steps 1, 2, and 4 as well. Before that, the computer was really just doing step 3, more or less. Now it's actually helping with abstracting, and it's helping with interpreting as well. So I'm hoping that this will work, but I'm slightly nervous this might not work. I was going to show you another example. This is a typical thing we want people to be able to do. It's like, okay, so we got half the class to toss a coin, heads or tails, and to note down the result. And we got the other half to cheat by typing in, doing what I'm doing here, typing in heads and tails like this. And now we want to see whether the computer, if it's working, okay, can tell who's cheated. And the answer is, it can tell I cheated there because it ran a bunch of tests on the data and it reckons I cheated. Now, if I was a really good student, maybe I should I could do something like, let's do random, let's see. Actually, let me not do this right now, because I think I'll run out of time. Let's do random choice, and let's do something like random choice of H and T. So if I'm a really good student, I might try and get the computer to help me to cheat, to see if I can, in fact, let's see if that works. Okay, so what I've done is generated some random heads and tails from the random number generator, and I'm going to try and copy those in here and see whether we get a different result. I think it'll probably accept them with like that. So in fact, that passed all the tests. So students are amazed. If you send this to the teacher can tell you which student. Imagine this is semi-cheating. I've sort of not done the experiment. I wrote a program to pretend I was doing the experiment. But the fact that a teacher could tell who has cheated and who hasn't is amazing. The students are often amazed by this. So this is a very simple example of data analytics, sort of thing that would do credit card fraud detection, where you're looking at patterns of data. And it turns out that when you're a human, you tend to type them too evenly. And that is not really what happens when you actually toss a coin. So this is a sort of insight into data analytics that you won't find anywhere in traditional maths curriculum. Just doesn't exist. Needs a computer. You don't do this kind of analysis. You only do analysis that you can do by hand. And so this is a typical, very simple example of something that you want to be able to do in a curriculum. So if you remove the computer from the curriculum, you remove most of the modern context for mathematics and computation. You can't do biosciences, you can't do medicine, you can't do history, you can't do all of that right-hand column I showed you, because they didn't exist before computers were applied with mathematics. Because you couldn't do them, because you need mass computation. So if you therefore set the educational system so that you don't have computers, you will remove almost all the subjects you actually use mathematics and computation for in the real world. And so you end up with basically the wrong subject. It actually gets even worse than that. So when you learn mathematics now in a curriculum in the world, you learn basically all the wrong techniques. Because the techniques you're learning, well, let me put it this way. I had a teacher at school in England. It was actually an intriguing character. He was a friend of Alan Turing's, the inventor of computers. And he had a saying, and his saying was, maths is the art of avoiding calculation. And he was right. 40 years ago, 50 years ago, he was correct. You did everything you could to avoid calculating because calculating was very expensive. You as a human had to do the calculating. Now, we have machines that do the calculating so that it's incredibly cheap. So the techniques you use can assume very cheap calculating. And of course, there's a major technique we use today called machine learning. Machine learning is an algorithm that can only work when you have very powerful computing, which is very cheap. Machine learning does not appear in any school curriculum for mathematics anywhere in the world that I'm aware of, even though it is a core algorithm that we use now in the AI age. This is the reason. If you use a different computational tool set when you compute by hand, and it's largely the wrong one. Another very exciting thing you can do, by the way, if you have computers, is you can reorder the curriculum so that you do things that are conceptually harder later. This is not what happens today. So one question I often say is, why do we not teach calculus to 10-year-olds? Most curricula, calculus is 16, 17, 18 years old. Why is this? I think the basic idea, if I take this water bottle and I say, how much water is in here? And the concept that you can slice it into little cylinders and add them up to work out what the volume is, I think is amenable to most 10-year-olds or 8-year-olds. The idea you can make it smaller, smaller, smaller until it's more and more accurate and add them all up and you get the volume. It's actually pretty neat and something that most people could understand, most students could understand quite early. Why do we leave it so late? Because it's hard to calculate. There's this magic function called integrate, but you need a lot of algebra by hand to know how to use it. But once it's on a computer, you don't need to worry about that. Conceptually, this is not too hard. You can learn how to apply this technique, along with many others, much earlier. And there are other things many other things in the curriculum, when you look at it, that are in the wrong order. So the summary of mistakes that have been made around the world in thinking about maths education over the last 30 years is probably this. I won't go through all of them. On the left-hand side is what people have said is important, and on the right-hand side is how they've interpreted that erroneously. So, the basics of mathematics is not computing by hand. The basics of mathematics is running that four-step process with whatever machinery you have. Succeeding in education doesn't mean passing an exam necessarily. That may not be a good guide to success. You know, how to work, this is a very important one, this fifth one here. How to work the machine is not the same thing as how a machine works. So how you use a machine to get a result is not the same thing as how the machine internally works. I use a computer as I am here. I don't know how the computer works internally, but I use it. I drive a car. I know a reasonable amount about how cars work, but I don't know all the details that an automotive engineer. I use mathematics, I use computation, I use data science, but I don't know everything about how you would build new data science or how it works necessarily, how the computer is calculating it. That's okay. That's what happens when you get automation. You get different layers, and you need to know a different set of layers and how to operate those, how to work the machine, not how the machine internally works. And probably the worst mistake, well, actually these last two, the thing that governments always say to me is, do you have evidence this works? Well, no, because nobody's tried it. There are two kinds of evidence. There's innovation-led evidence, which many startups do. They try an innovation, they see whether it works, they go and get the results, they innovate again. And there's evidence-led innovation, which by definition, you cannot make big steps. If you need the evidence first, you can't jump. Most of education is in this second mode. You have to have the evidence before you can try anything, which is why it's stuck and the education doesn't move forward. So, and a key mistake is the idea that doing something that's lower risk is not making a change. It may be lower risk to the government minister, apparently to not make a change, but that doesn't mean it's lower risk for the society or for humans against AIs. Sometimes we need to make changes, and in fact, that's the lower risk route. So another thing I just wanted to touch on for a moment is, with AI linguistics, do we still need explicit code? Do we actually need to write programs? Do we need computer science? And my answer to this is, yes, you do need abstraction. Abstraction is very powerful as a precise way to communicate and think about things. But of course, with AIs, we have many new ways to generate that. You don't need to necessarily write code from scratch. You can actually get it produced. So one of the examples I want to show, if it works, is Wolfram language is the language we've been building for 36 years. It's kind of more than a programming language. It's a way to sort of represent ideas in computation at a high level. And it's a sort of way to communicate human technical ideas as well. And so just to give you an insight into what we've been trying to build, we want to represent all of these things in the same way. And you can see that all of these elements on the right, you can see this is what the element actually is. This is the code that represents it. So we have the most general representation of computation that exists in a systematic form, whether it's maths or whether it's the interface that, like this interface, is represented in this way. And that gives tremendous power to computation. So this is a new thing we have called Notebook Assistant. And I typed in, I won't try and run it live because of my internet problems, but I typed in, make me a program to show EU countries each marked with their GDP per person. And so it wrote me this piece of code. And if I evaluate it, whoops, we still have our data problems. Oh, this is frustrating. Let me Let me just quickly see whether I can affect a change here. I think we may be out of luck, but I really wanted to show this. Something let me just see if I can quickly, I tell you what, I'll come back to this and try and show it at the end if I can. What I wanted to show was that we can actually produce this code straight out, and it just evaluates. But having the code is actually quite useful because you can go and literally go and adjust the code and make it work. And let me at least show you this, since I have this up. This is an example of a typical thing you might do. You might ask it, plot the most direct route from London to New York on a world map, and then let us, actually display this here, which you can do, as you can see, kind of easily, and it's a very short piece of code to do that. So this interplay between abstract code and linguistics, I think, will be very important in the future for optimizing what we do, and particularly in some of the more modern uses of computation. One of the things we've been doing the last year or two is to sort of use symbolic AI of our Wolfram Alpha and put it together with generative AI. They have very different characteristics as to what kind of runs well and not so well. And so putting those together gives you really tremendous power. So on the educational front, I built a startup called computerbasedmath.org, and the idea is to build a core computational curriculum that assumes computers exist. And a typical thing that we deliver out of that might be a module, and let me just show you these modules here. Oh my gosh, we still do have the gremlins today. Let me see if I've got this up anywhere. Let's try this. And there we go. For some reason, there we go. This perhaps might show you. So this is a typical module, which was how fast could I cycle a cycling race? And what we want, and this is the teacher edition, so it shows with the orange boxes to help the teachers actually command the students if that's necessary. And you can see here we actually have real models, and we want to actually have students interact with complex models and think about how mathematics is useful to a practical hard problem like this, and then work through how you'd use it. So that's a typical kind of deliverable that you might have. Now, the really exciting thing recently, of course, is that one can get AIs to act as the teacher on this. And so this is an example of, in a sense, an AI asking, so you could, as a student, what will the population of Doha be in 2100? The AI is then helping to tutor the student using our technology. And this is actually really powerful, particularly for this modern kind of mathematics that we are trying to get to. I wrote a book called The Maths Fix, where I detailed the proposal that I'm trying to make to achieve this fundamental change in education. And although I talk a lot about mathematics, the key thing to know is that this is coming for all subjects. AI is changing the real world out there. Mathematics was changed decades ago by computers, and yet we still haven't changed our education. So we better wake up, because we haven't done this for decades for mathematics. We've now got not only mathematics to change, but every other subject too. If we have a new computational curriculum, what can we achieve with this? Well, I think we can achieve first-rate human problem solvers, not third-rate human computers. If you're a human, don't compete with what computers do well. They compute. That's what they do well. Let's not try and have humans compete with that, because they'll lose. What we need humans to do is work a level up, be the managers of the massive computing power we have to get better answers, to optimize human-computer decision-making. And this has pretty big consequences. You know, at the moment, we have a big computational divide across society. So I want you to imagine back in the 18th century, when most people could not read and write. The idea was that a few people at the top of society could read and write, but most people couldn't. And there was a big movement to try and change that, which a lot of people opposed. And that's what led to mass literacy that we have today, where most people, certainly in developed countries, almost everyone can read and write. I think we are now in a new era where we need people to be able to function with computational understanding, what I call computational literacy. And if you don't have that, you have a big problem with enfranchisement across society. And we see some of this emerging in our democracies. If people make decisions on the basis of computational results, as they do, even in the pandemic, and most people don't understand how that's been arrived at, they get very suspicious of it. They don't understand. They don't know how to question it. So that causes big problems in society. So we absolutely and urgently need everybody to be educated enough to avoid this computational divide. And that's why I call it computational literacy for all, which I think we have a big help in delivering now with modern AI. So what we really want to achieve is education reformed for the AI age and maths reform as a template for that. And hopefully this is something that we can now really move towards. I think there's a lot of pressure to make these sorts of changes. Before I close, let me just have one quick attempt to, to try and just see if I can find out what happened here, the gremlin, and see why, for some reason, we were not getting a connection here. And if I can rerun any of those things, let's see what went wrong here. But I'm not sure why this hasn't run, but I think we've got some connection problem here. Anyway, I will close on that rather than trying to rerun it at this time. Thanks very much indeed.